Hi everyone, this is Nick Fryer, and today we're talking about Physics 2, Lab 5, which is magnetic braking with Faraday's law. So just as a quick introduction, we did an experiment where we dropped a magnet through a tube of aluminum foil and timed how long it took to get through. We simulated the system using GlowScript and VPython, and then we compared the two models that we had. In conclusion, observationally for the magnet to fall through the tube, it took about 1.204 seconds, but the same conditions in the simulated model took only 0.33 seconds to fall, so much faster. And the model took about the same that it did observationally when we changed the magnetic dipole moment to be much, much higher at 5.62 ampere meters squared. So just as some quick fundamental principles, first is Faraday's law, where noting that phi just means flux. The closed integral over the loop is given by the negative time derivative of flux, where flux is just the amount of magnetic field that passes through some area. And the rate of change of magnetic flux, or at least the magnitude of it, is given below. So it's a relatively complicated equation, but easily put in the computational model. Just noting that if some current is induced, it's going to flow in the same direction as the electric field that is induced. Also, there's magnetic force on a loop of wire, which is given by I delta L cross B. And at least the magnitude, just by cross product laws, is given by I times 2 pi r B sine theta, where 2 pi r is the length around the loop, the circumference. And by Newton's third law, that means that the magnitude of the magnetic force on the magnet is exactly equal to what we see above. And Ohm's law says that the change in magnetic flux would induce a current. And again, by Ohm's law, since I equals V over R, and then we have V equals the EMF, which is the negative time derivative of the flux once again. So just a quick diagram, we have our magnet falling through. The force on the magnet that's exerted by the loop is exactly equal in magnitude and opposite in direction to the gravitational force on the magnet, which means that the magnet falls at the same speed throughout, since the net force is zero. The system as the magnet, surroundings is kind of everything else. So the Earth exerts a gravity, and the aluminum foil exerts the magnetic force. Again, noting that the blue arrow, the electric field, goes in the same direction as the current throughout the entire loop. So the experimental procedure, we mark the north pole of the magnet. We measure different dimensions of the tube, and then we drop the magnet into the end of the foil tube, record how long it takes, and average that over 5 trials. Then we build the computational model to simulate the system and compare the real life and simulation models. So just a very quick data collection video. You can see that when we drop it through the top, it falls a lot slower than what we would expect. So the experimental data, the length of the tube was 46 centimeters, and the total radius of the tube was 1.65 centimeters, broken down as you see above. The magnetic dipole moment, which was already measured from Lab 3 with the same magnet, was 1.833 ampere meters squared, and the mass is 0.023 kilograms approximately. And you can see at the bottom the time trials that we ran and how we got to the average time of 1.204 seconds to fall through the tube. So computationally, we created some constants. We then created both the tube and the bar magnet. And then we used a function to calculate magnetic field of the bar magnet, as well as the time derivative of the flux, to ultimately get the time that it takes to pass through the tube. So the simulation results, when our mu was the same as it was observationally, it only took 0.33 seconds to fall through the tube, so it was very quick. And we had to increase the mu all the way to 5.62 ampere meters squared to get it to the point where it fell through at approximately the same time that it did observationally. So clearly there was a lot of error. The time that it took observationally was so much higher than what GlowScript said it should take. Likely this is due to two major things. One is human and measurement error. The meter stick and the camera are just inherently inaccurate when they're used to measure things like this. But also there could have been a lot of contact between the magnet and the tube while the magnet was falling, which would slow it down, as well as just general air resistance. So if the resistivity of the conductor was reduced to practically zero, this would mean that there would be no resistance, which would lead to a large induced current since I equals V over R and R is very small. So the magnitude of the force, which is directly proportional to the current, which would be now much higher. And by Newton's third law, we have that the magnitude of the force by the loop on the magnet would also be amplified at the same amount. So the F net, which is Fg, which doesn't change, plus the force of the loop on the magnet would get much higher because the force of the loop on the magnet is now higher. So the force would point in the plus y direction more, meaning the magnet would fall slower. However, alternatively, if there were holes in the tube, this would mean that certain areas are no longer truly rings and loops, and therefore this would lower the induced current, which would mean that the magnitude of the force is now lower, which by the same reasoning as before would mean that the net force would point less in the plus y direction, and therefore the magnet would actually fall faster and take less time to fall through. Thank you, and I hope you enjoyed.